All right, great. Then I'll get us started here. I have the pleasure of introducing our Emmy Seminar speaker today, Professor Hannah Budinoff. Hannah is an assistant professor in systems and industrial engineering at University of Arizona. She has her master's and PhD from UC Berkeley, and her bachelor's in mechanical engineering at University of Arizona as well. So her research in general focuses on automated geometric manufacturing analyses, focusing on additive manufacturing processes, designing and developing design support tools, which we'll be hearing more about today, and also a focus on engineering identity and engineering skill development. She actively collaborates with folks across government, academic, and industry positions, and her funding reflects that with funding from NSF, NIST, and DoD agencies. So very pleased that she was able to join us today, and I will turn it over to her for delivering our seminar talk.
Great, thank you so much. And thank you all very much for coming and joining me today. I'm happy to take questions as I go, so feel free and stop me. So when we think manufacturing, it's actually a little bit top of mind. We've seen a number of headlines that have talked about manufacturing. Of course, not all of the reasons that Boeing is in the news have to do with manufacturing, but some of them do. So there's been various quality issues, whistleblowers coming out and saying that some of their processes for dealing with deformed parts because of various manufacturing processes are inadequate and could lead to increased load beyond what they say in some of their documentation. Tesla has been plagued with some manufacturing issues of various kinds. So I think that this isn't a surprise to many of us with mechanical engineering backgrounds. Doing manufacturing is not easy, and incorporating an understanding of the manufacturing process into our design decisions is perhaps not intuitive and can often be challenging because we don't have adequate tools or methods to do it well. So that's kind of what I'm going to be talking about today. So I'll start with a little bit of specific background that's been motivating for me, which is some work that I did in grad school and shortly after, specifically interviewing startup employees, startup founders, and startup employees about their design for manufacturing practices. So this is not exactly the same as industry practices, but I think that there's some natural synergies across the two. So Dr. Kramer and myself did an interview study where we recruited 12 employees, 12 engineers at various startups. It's a little bit of an eye test for those of you in the back of the room, but you can see that their titles varied: CEO, CTO, design engineer, senior mechanical engineer. Job experience, the lowest was 2, the highest was 12, so moderately experienced, not extremely, but still many years of experience. And then the sectors were pretty widely varying with number of size of employees going up from 1 all the way up to a pretty successful startup with over 1,000 employees. So we interviewed them. What does design for manufacturing look like for you? When you're doing design, how do you consider manufacturing, if at all? Is it important? Is it not important? So the answers that we found were interesting. We found a variety of kind of design for manufacturing practices. These might not be things that came out of a textbook, but they were ways that the engineers told us they considered design, they considered manufacturing during the design process. So we categorize these into 4 basic processes, either considering different manufacturing processes before they had decided on a particular manufacturing process to use, understanding manufacturing constraints, identifying manufacturability constraints, so more geometry specific, and then troubleshooting manufacturability problems. So you can see that in increasing lightness of the blue color, that's increasing specificity to their particular product. And then across the top axis, we have a general kind of progression, design progression. Of course, it's iterative, but from initiation, we found a big difference between when they had CAD and when they didn't have CAD in their processes, and then after the first large production run. So we identified common practices and mapped this onto these 2 axes. So I'll read some of these. Consult external resources. That might be a website, it might be a textbook. Identify flexible manufacturing processes that would allow them more room to maneuver in the design space. Use cost modeling. Use personal knowledge of manufacturing processes. Incorporate existing designs and use them as a baseline. Consult manufacturing experts for feedbacks. Conduct design reviews with manufacturing experts. Utilize CAD manufacturing simulation tools. And then actually try and get experts to help with production problems and testing the product to verify performance with as manufactured properties. So this kind of encompasses from all 12 engineers, pretty much everything that they said could be mapped onto one of these specific practices. So what do you think? Do you think that their use was spread over evenly over these? Are there some that they were used infrequently? Any thoughts? What do you do in your design processes? Yeah.
It seems like there's a small amount of CAD-based simulation that's going on here compared to the other categories. There's
Okay.
not a lot of, it doesn't look, at least to me, like there's a lot of simulation.
Okay, so this is across the top axis now, we have all 12 of our designers. The color now indicates the number of instances where they described this process, where they described using this DFM method. So I'll highlight 3. The first one is consult external resources. This is something like I looked at a textbook, I looked at a blog. That was actually by and far the most consistently and kind of the most used process. But it's fairly basic, I would say, and also not very specific to a particular part or geometry. Another one, use personal knowledge of manufacturing processes to design manufacturable products. People spoke about taking a machine shop class and understanding what could and couldn't be manufactured just based on their hands-on experience with a particular process. Okay, then finally down here, we have kind of 2 related ones that were pretty widely used. Consult manufacturing experts for feedbacks and or quotes on preliminary content, preliminary concepts, and then do design reviews with manufacturing experts. These were pretty consistent, where people did this a lot. So, you know, obviously there's some pros and cons for each of these. At startups, they're fairly resource constrained. So they didn't have tons of money to go out and do lots of different, you know, reviews, lots of pay for a lot of different simulation, a lot of different analyses. So they used their potential vendors to give them feedback. It's a nice, efficient process, but they were pretty dependent on the quality and the time that these vendors were willing to give them. They trusted them to have the expert guidance, and they were really reliant. The success of their products was really reliant on the quality of the feedback that they got. So there's some good things and some bad things associated with this, but by and large, the feedback that we got from designers was this is a magical process I discovered by myself. Externally consulting with manufacturing experts basically was an organic process that they discovered for themselves as being the most effective DFM practice they could employ. It was not very little internal to themselves, very little analyses that they did internal to their teams. Relying on experts was this kind of viewed as this magical, excellent end all be all for DFM. One quote that we had from a participant was, "You just need to have scars. You have to have the scars of messing up." And they, meaning her mentors, are like, you will get those. But right now, in order to save your company, your startup company, you don't have the time or the money to afford those scars. You need to look at a guy that has seen that problem for 20 years. So from this, we understood that there was a lot of respect for the expert feedback that external vendors could provide. But one reason for that is because they looked to them for product-specific feedback, feedback on their designs that was based on their CAD models, their CAD drawings. They had essentially no other way to get feedback that was specific to their designs beyond relying on these external vendors. It was their only option to get part-specific feedback, and they really valued that. It needed to be specific. So looking at a whole on all of our interviews, we can extract some of their design, the designer needs. One is giving feature level, geometric feature level feedback that's very specific to their design. This section is too thin, this section is too thick, this will be difficult to access, et cetera, et cetera. They really wanted iterative rounds of feedback. They valued working with vendors who would not only respond to a single emailed drawing, but multiple rounds and would work with them iteratively. They really wanted the feedback to be based on deep process expertise. And then they wanted to be able to associate likely production problems and tie them back to product functionality. It's not just enough to say, oh, there's a problem, unless you can associate it with a delta in the final product's functionality. You know, this is likely to affect the stiffness in this way, this will affect your total stack up in this way, you'll have this type of assembly problem, whatever. So they really wanted it to be associated with predicting the deformed geometry and associating it with product functionality. And then in addition to just yes or no, this product can produce your geometry, they wanted some cost information and potentially some sustainability information. Some of the startups were in a kind of sustainable energy type space, and so that was a consideration as well. So these are some of the designer needs. Let's talk about what exists for them. We have all these methods that the designers felt were organic, that they emergent practices that they developed through their own practice, their own experiences. If we look in literature, there's a fairly narrow range of what's considered DFM tools. So this is a mapping that I've adapted from an academic paper that basically puts design tools into 4 buckets, depending on when they're used. In conceptual design, you might use design heuristics and principles. There could be some cost estimation tools. In design embodiment design, there's some design guidelines, minimize the amount of material you might use, etc. In detail design, we get into design rules and specifications, which might give you the maximum feature size, for example, of a particular manufacturing process. And then process planning guidelines for process planning, optimization, and also doing some simulations. So very, very detailed and nuanced simulations of a particular manufacturing process. And you can see that there's increasing levels of specificity as we go along, which makes sense, right? There's not really a way to do a detailed simulation of your machining process if you don't really have a concept that doesn't make sense. So obviously these have increasing levels of specificity. But something that we see is there's a really big jump here. If you look at the design rules and specifications, the design guidelines, these tend to be just simple heuristics. They tend to be very hand wavy. Keep your pockets to approximately this depth without a lot of specific guidance. It's also generally just a rule. It's something that you can manually check, but it's not easy in many cases to actually evaluate this for a CAD model. Whereas for process planning and process simulations, that typically needs some sort of CAD model as input. So we see this big disconnect in this middle to kind of early stage design where you might have a sense of what your geometry looks like and should look like, but you don't have tools, existing DFM tools that can take that as input. So in general, we see this mismatch between designer needs and current capabilities. If we look,
quick question,
yeah.
just on the last slide,
yeah.
Where would you normally find that the process gets, maybe not the parameters, but the process itself gets defined?
The process like gets selected, like I'm going to do machining versus something else, probably around here in embodiment design. So detail design, this is like I'm going to have part A and part B in embodiment design, and then in detail design, this is the geometry of part A. It will be yay big, have this kind of feature.
And it will be sheet metal form.
Yes.
Through the.
Yeah, but embodiment design, I think, is when you start to at least have a sense of the process, but not the exact size of each of the features. This is where you could do a back of the envelope sketch, give the overall feature size, do a rough CAD model, but not finalize.
Thank you.
Okay, so mismatch between designer needs and current capabilities. If we look at the various solutions in that bin, DFM kind of things, heuristics, process design rules, there's also a couple of software that exists. Our Priori is a startup that I think was founded in 2018 or thereabouts. DFM Pro is another software. Let's look at how they map onto designer needs for part-specific results, cost, manufacturing, being able to predict a deformed or as-processed geometry, being compatible with early design, and considering many different manufacturing outcomes. So yes, academic heuristics and guidelines, they're low cost, they're easy to use in early design. Existing software can give part-specific results, but it is not low cost. The subscriptions actually can be pretty substantial. It's their entire business model. They're not going to give it away for free. They typically don't predict manufacturing geometry, but they do basically predict compliance with the design rules, and they can give estimates of cost. So that's what they can provide. They take as input a fully defined, finalized CAD model, and in many cases, they don't consider that many manufacturing outcomes. So what I want to do is fill this space. I want to develop DFM tools that can check all of these boxes and meet designer needs. So ultimately, my research goal is to develop computational tools that can fill this gap, that can connect designers easily to manufacturing knowledge, so that they can get better manufacturing outcomes, they can design and get better quality parts. And then software, the software side of it is interesting to me too. I want to develop software tools that can support the designers, and then I want to assess how these tools can actually be used in the engineering design process. So today I'm going to talk about 3 studies in that broader umbrella category. I'll look at the effects of DFM tool modality, basically trying to evaluate how computational tools compare to heuristics. I'm going to look at surrogate process models to see if they can provide reasonably high fidelity feedback in a faster amount of time. And then I'm going to look at sustainability metrics and how these can be incorporated into decision-making processes. So let's first talk about effect of DFM tool modality. So this is some work that came out of my dissertation. Basically, I was a TA. I don't know if we have people who have been TAs in here. I saw a bunch of poorly designed and poorly manufactured parts for the class that I was a TA for. And I would see the same failure modes. We asked students to just 3D print a part. I would see the same failure modes again and again and again and again. And so I decided to try and categorize these. I would look at the parts that they submitted. They tried to print a model that really should have been printed with SLA. The resolution, the minimum feature resolution was too high. They printed parts with ABS that would warp pretty substantially. You can see there's like that much curl in a corner. They printed parts at ridiculous orientations that actually toppled over with no support material, that toppled over mid-print. So I categorized these and basically tried to develop a DFM tool to evaluate them. There's already some existing DFM tools that fit into that guideline type realm or heuristic type realm, where they give you guidelines. This is called the DFAM worksheet. And it tells you, it gives you some guidance about the thickness of different features, different types of forms, having unsupported features, and so on. So I adapted this and made a version that was better aligned with the failure modes that I saw based in our students' prints. And then I made a computational tool that evaluated compliance with those rules. So this is a part that's been uploaded. These are the errors that I categorized. So whether there were small features that were too small to be printed viably with 3D printing FFF, the computations that you see are in real time. So whether or not there's overhanging features, just based on the STL normal vectors, whether or not the part was likely to wobble over and tip over, and then warping and rough surfaces as well. So as I said, the computations are pretty much in near real time, and students could evaluate compliance with those rules. So my goal is to look at the effect of modality here. We gave participants a DFAM challenge where we asked them to redesign this basic pencil holder geometry that I designed specifically to be slightly difficult to print. I had a number of features where there were basically very thin walls, like 0.1 millimeter thick on the base plate. I designed it so that the orientation was actually somewhat difficult to select if you were worried about warping, which we were printing it purely in ABS and unenclosed printers back in the day. And then I assigned people to 2 groups. I assigned them to use the worksheet, or I assigned them to use the tool. And then I looked at various metrics of their outputs. Creativity, which was measured using usefulness, subscales of usefulness, uniqueness, and elegance. I counted the number of manufacturability violations that they had, features that contrasted with what the tools told them to do. I measured their total design time, and then they responded to a survey that measures task load. It measures how hard the task was for them. So the designs that we asked them to submit were basically the orientation, the build orientation, and the redesigned part. So we asked them to consider both at one time, the geometry and the orientation, the process plan. You can see a pretty wide variety of responses. They fit into a couple of different categories. A really common solution was, let me make a box instead. I'm just gonna chop off the interesting features. I'm just gonna print a box up and down, straight up and down. Interestingly, a number of these designs actually introduce new design problems by having too thin of walls. Sometimes they would orient them like this, requiring a vast amount of support material. But then we saw a number of slightly more creative solutions where they basically chopped off a part of the back end or chose a really interesting way to orient the part that was able to preserve more of the initial geometry while still being more in alignment with the design guidelines. So here are the 4 outcomes we looked at. In blue, we have creativity. Green, we have number of manufacturability guideline violations. And here we have the time to complete the task. And this is the task load. So essentially how difficult the task was for students to complete. So a couple of things that I want to mention. Time to complete was actually pretty similar. There weren't really big differences. Number of guideline violations, that's where we saw a large statistically significant difference, where students who use the software were better able to identify some of the violations that occurred. Task load was pretty similar, and something that we saw with creativity was actually there were more highly creative designs of students who chose different orientations. The tool wasn't actually as important for creativity. What was important was students exploring different orientations and recommending different orientations, that if they considered that as part of their design space and integrated the manufacturing process into their design decision-making, they were able to create more elegant solutions to the design problem rather than just having basically a shoebox with 4 holes in it, right? So in this upper corner here, we have a number of solutions that were coded as highly elegant and had high usefulness. And all of the 10 in the upper corner that had the highest scores with these, all 10 of them had alternate orientations. They weren't just a box standing on the build plate, they were actually oriented at a slightly different orientation. So in AM, we can consider this aspect actually as a way, again, of expanding the design space. If we allow designers to consider their geometry and the way to orient the part at once, they can come up with more creative solutions overall. Okay, this actually echoes back to the interviews that we did with startup founders. One quote from one of our most experienced engineers who was working in the healthcare equipment and services industry said, in some ways, considering manufacturability, it limits your thinking because you know what is actually possible. But in some ways, it actually expands your thinking because it's like, okay, well, they can do this and that'll spark other ideas and you can potentially do stuff with this. So I think manufacturing is generally considered as a constraint, right? It constrains designs, but in some interesting ways, it can actually expand the design space and it can provide you with inspiration and different ways of making one geometry. With the overall geometry, it might look slightly different, but there's various ways that you can actually create it. So I think there's a really interesting association between manufacturing constraints and creativity that I'm looking forward to exploring kind of more in future work. In general, going back to the high level topic, my question was computational tools, how do they actually compare to simple heuristics like we saw with DFM? In general, we saw that the time and task load were similar, but that there's this interesting connection between creativity, alternate orientations, alternate process plans. And then in future work, we're looking to explore this for other design tasks and for a broader range of experience level. This was students, so it would be interesting to compare this with more industry practitioners and look at also long-term acceptance and use. All right, so I'm gonna move on now to the next topic, which is higher fidelity DFM feedback. So for this, we're gonna transition to a different process. How familiar are people with laser powder bed fusion? Yes, familiar, not so familiar? Not so familiar. So laser powder bed fusion is similar to polymer 3D printing like you saw, but instead of taking a filament of a material, of a plastic material, it has a powder bed, and then there's an energy source that essentially melts the powder together. But it still works in a layer by layer process and can form fully dense or pretty much fully dense parts additively. So in the AM typical workflow, there's actually important use of process simulations to compensate design. So you'll take a CAD model and you will use FEA type tools to predict how the part is going to distort. You have relatively cool powder that's pretty insulating for the part, and then you introduce your hot energy source. Your melting powder is a really thermal process. There's high thermal gradients, really hot parts and really cold parts of your build. And this can create issues with distortions, it can create issues with cracking, and your part can actually fail to build. You'll have a big crash in the middle of a build, for example. So simulations can help guide designers to compensate their designs, to selectively shrink or expand portions of their design so they print with better quality. And then it can also help them select a build orientation. So these are kind of design tools, but if you notice, the geometry is essentially fixed. They're not considering any geometry changes. They're not optimizing the design in any kind of iterative way. So my goal was to do earlier in the design process, when the geometry can be changed, how can we help designers actually make better decisions? So similar to the DFAM worksheet that you saw before, there's been a version of it that's been proposed for powder bed fusion that gives guidelines for overhangs and types of cross section, surface finish, etc. And then you self-score this. You have a geometry, you go through the worksheet, and you give yourself a score. If we look at a variety of different sources, and we're trying to minimize part distortion and build failure, just have better quality parts that aren't going to fail to print. Some guidance is avoid large solid volumes. It's harder to print big chunks of metal than it is to print smaller chunks. Use fillets, minimize the size of unsupported downward facing surfaces, and avoid abrupt changes in the thickness of your parts. So those are some general guidelines, but again, all this guidance is fairly ad hoc. It's based on some anecdotal evidence, and designers have to apply these types of rules themselves. So my background in my dissertation looked at computational geometry approaches, and there's a ton of different ways that we can analyze part geometry and quantify differences in part geometry from the computer science and computer graphics field. So broadly speaking, I'll just refer to these as shape descriptors. There's ways of describing and quantifying a part's shape. At the most basic level, this is something like area, right? That's an easy shape descriptor for us to get our heads around. But then there's weirder things like surprisal, which has information about how fast a contour changes. There's various metrics that you can quantify for the horizontal distribution of material. So I found a bunch of different shape descriptors and tried to, and it generated some new ones based on the guidance that you saw on that last page. How can we predict, how can we quantify changes in the shape that might be correlated with bad manufacturing outcomes? And so in order to do this, we restricted ourselves first to 2D cross sections, so axisymmetric parts, because I wanted to be able to analyze one cross section, calculate the shape descriptors to describe the volume with only a single image input. So we're expanding this to extruded parts, more complex parts, but this is just our first data set. So these are the 2D cross sections. We can calculate area, right? You guys can imagine how to do that easily, but the other things take a little bit more work to calculate, but we calculated a set of 92 shape descriptors for each of these, and we have 324 variations. So we varied the part size and then the geometry itself. Then in order to predict the manufacturing outcomes, we did FEA simulations of the laser powder bed fusion process. So we simulated with an EOS machine on titanium using a commercial package that employs a lump layer model. We did consider plasticity and had some calibration factors that have been experimentally derived and validated to give us pretty good agreement with the simulation and the prediction. So from these complex fields of distortion, we selected a single value for each part, max distortion. This was just our first way of estimating the manufacturability of the part, considering that high max distortion values would likely be associated with parts that have high thermal gradients that may fail during the build process itself. There's other metrics that you can choose. This is just the first one that we did. Something that I'll note here, these are relatively small parts, about handheld size parts. 1 to 90 hours of computation per each part based on the FEA model. So our goal is to develop a surrogate model that can do this faster. So that's what we did. We analyzed each cross section, generated a list of shape descriptors, narrowed down the shape descriptors that provided us with the most information. As I said, made a CAD model, did the simulations, extracted the max displacement, and then trained a made a machine learning model to do this faster. We used Gaussian process regression, but we evaluated a bunch of other options using auto sklearn, which is just a nice Python implementation. So in the end, we were able to develop a fairly accurate prediction model. So I have test data. We used about a quarter of our data as test data and the rest as training. So you can see pretty good agreement between the predicted values of distortion and the true values. So again, this is taking a 2D cross-section of just the geometry, no other information. We're able to predict the max distortion of that part with about 0.068 millimeters. So that's a couple of thousandths of an inch of accuracy. So fairly good accuracy for a pretty good range of different geometries and parts. We wanted to get closer to design guidance, so we looked at the types of shape descriptors. We looked at the permutation importance. So basically, if you allow to vary a single descriptor at a time, you can see how much it changes the output. We actually interestingly found that surprisal, which has to do with the contour shape on the build plate, that was the most important. The connection to the build plate essentially was the most important part of the geometry beyond area or some of the other things that we thought would happen. But in general, all of the highly important features were associated with the distribution of material along the kind of XY axis, which makes sense with some of the guidance that was given, but now we're able to actually calculate its importance. And this can be translated back into guidance for CAD. Essentially, we can take this information and incorporate it to a plugin. So a designer would be prompted, you have a really high value of X shape descriptor. We suggest you change X feature, something like that. So right now we're at kind of the preliminary phase. This is based on a conference paper that my PhD student and I wrote, but we think that there's really good promise here to use shape descriptors as the basis of more explainable ML methods. You can do this with a deep neural network type ML model, but the problem is it's difficult to translate that backwards to design guidance. Essentially, you could have a really good prediction, but the designer wouldn't have an actionable idea of what to change. It would just be, oh, high distortion. Okay, what should I change? Should I scale it down? Should I adjust this part, this part, this part? It's difficult to do that with more, with deeper ML methods. So using our feature-based approach, it's more interpretable. But we had good accuracy. We think that this also is interesting because as image input, using a 2D input can be helpful for earlier design feedback when a designer might have a sketch of something, but not a fully fledged CAD model. So we can use that sketch type input directly and come up with some sort of prediction. We also think that there's a really good opportunity here for these shape descriptors, these kind of ensembles of shape descriptors to be used for different manufacturing prediction problems. We could use this to predict build time. We could use this to predict castability. We could use this for essentially anything because you're just capturing a lot of the geometric information about a part in a very, very concise way that can then be used as input for really any ML type application. But something that I want to highlight is it's a little hard to say how designers would feel about this feedback. Are they going to trust a surrogate model? I don't know. I think it has a lot to do with the interface design and the setup and the use case. So that's something interesting for future work.
And can you real quick talk about, so I'm sorry,
No.
rushing for time here, but
Yeah.
the scan path generation of the lasers, because that will affect
Yes.
largely how the thing's going to print. What model or system did you use for scan path generation?
Yeah, so that's a good question. In ANSYS, there's different levels of accuracy, and then they come with a trade-off of speed, of prediction speed. So for this lumped layer model, it's a single, I need to double check with my PhD student, but I'm pretty sure that what we modeled was a single layer at a time. So it doesn't consider the effect of one particular scan path versus another. You're right that it does matter, but this can get us part of the way there
Yeah.
with a simulation time that's tractable to make hundreds of simulations.
Absolutely, I was just thinking like for like distortion mitigation, like that's a common strategy to like
Yes.
spread out your scan path.
Right, but
From the, yeah.
yeah, I think
scan path.
it's also a question of where do you want to do a lot of your kind of design work? Do you want to do it and change the geometry, or do
Or
you
the
want to do it to change the parameters? Ideally, maybe you change both at once, but this is just trying to get more at the, let's change the geometry. Yeah, great question. Okay, so then I'll move on to this last piece. I've talked about manufacturability a lot. Let's talk about sustainability. How can we incorporate some sustainability metrics into the design for manufacturing process? So moving back to material extrusion to FFF, there's been various life cycle assessments for FFF, but something that we see that the 3D printing process itself is fairly energy intensive and can actually drive a lot of the total impacts. So these are various impact categories, global warming potential, et cetera. You can see that the 3D printing process is responsible for a majority of the impacts. So, however, the energy consumption actually varies widely based on the part that you're printing and the printer and the specific use case. Reported values go from 0.36 all the way up to 612 megajoules per kilogram for specific energy. So a ton of slop in that estimate, right? If I try and ask you how much, can you try and reduce the energy consumption by 10%? It's going to be difficult for you to know if you need to shave off 60 megajoules per kilogram or 0.3, right? To have an order of magnitude, multiple orders of magnitude there it's a lot to work with. So we need to be able to more easily estimate energy usage. That was the motivation for this project. So my PhD student David and I went through literature and found existing models. These are all empirical or semi-empirical models that estimate energy usage for FFF based on various factors, mostly empirical factors. Some things to note here are important terms that you'll see are the temperature of the extruder, temperature of the build plate, and then the production time, TP. There's also some models that incorporate the total amount of printed volume. So we gathered all of these models and we wanted to see, they were all developed for a single printer and a small number of part geometries. So these are difficult to use for general design guidance. So what we did is compiled a fairly large database of data from literature and from our own experiments, 374 different energy measurements of FFF printing for a pretty wide variety of different geometries, so a fair number of small parts, but a fair number of large ones too, various materials, various different printers. This is actually a log scale. It looks fairly normal, but it's not. It's pretty skewed to have most of the values in between 0.1 and 1 megajoules. So relatively short, 10 minutes, it's 10 to an hour, maybe 10 to an hour, 10 to 2 hours, something like that, type prints, not really, really long prints. So we split this into a training set and a test set, and then refit the empirical values associated with the various coefficients here, just to give each model an equal chance. Like I said, each of these models was developed for a single material in most cases or in a single printer. So we wanted a more general model. We evaluated the performance. The performance is pretty good, and it's similar for the different models. This is a log scale, so again, it's a little difficult to see the difference in the performance. If we look at the performance metrics, mean average error, mean absolute error, root mean squared error, R squared, et cetera, we see that some of the models actually are garbage. Please don't use this model. But the rest of them have R squared values around 0.94 and have relatively small average errors. If you know the time, if you know the build time, if you can plug that in, then I can give you a pretty good estimate of the build time. But that's difficult. If you were trying to get design guidance, how are you going to know the build time, right? So we used a general estimate of build time and then plugged that in, and we got worse performance. Unsurprisingly, the energy consumption depends heavily on the build time, so the performance of the models went down. but we still decided to go with these estimates. We improved this slightly because we incorporated our energy estimates into Cura. This is a really commonly used slicer that prepares a 3D model to be printed. So we plugged in these equations and used Cura's build time estimations, which actually go through the G code, estimate accelerations, decelerations for the motors. And so we found that the estimates are pretty good in terms of build time. So let me show you that tool. So it's actually pretty fun to do. I've loaded one part. I have the Prusa. This is printing in PLA. I'm printing with 50% infill, a fairly normal layer thickness of 0.15 millimeters. The total amount of energy usage is about 4.5 megajoules of energy. But now that we have it, we can decide in real time what to change. So, okay, this is the interactive portion of the evening. What can we do to change the energy consumption? We want decent quality of this part. It's a bracket for a bookshelf. What do you want to change?
Lower your input density.
Lower the infill density, how much?
20%.
20%, okay. So the Cura slices, it re-estimates the build time, and then our model will update once it's sliced.
Is that little point up to just the initial like startup energy of the machine that it starts?
Not exactly, it's more of an empirical model fudge factor. We're trying to move towards a better model that is that. We can do better estimates of predicting how much build time, how much warm up energy will be consumed versus printing energy, just based on the physics of the process. But it's affected by different factors. Is there an enclosure? How big is the build plate? What's the temperature? Yes. So we're working on an improved model. Wow, this is slicing really slow. This normally slices in about real time, so I'm not sure what's happening. Oh, okay, I'm gonna turn off support material. Yeah, okay, so the computation, it takes on the order of about 5 or 10 seconds, depending on the complexity of the part and the G code that has to be generated. Okay, so we went down a little bit. Any other suggestions?
Resolution.
Say it again.
Resolution.
The resolution, change the layer thickness. Up or down?
Up.
Up, okay, so we could go to extra fast. And then we'll see how that affects the build time. Okay, and energy consumption, so actually that's in terms of the variables that it's sensitive to, that's what it's most sensitive to layer thickness. But you can play this game and change various parameters and try and optimize for yourself as part of your workflow. And it's just something that you can download if you want. I have the QR code. You're welcome to come to our GitHub page. You can pull feature requests. You can download it and you can try it for yourself. So this is a work in progress. Like I said, we're trying to make the model a little bit more accurate beyond what it is and to incorporate more of the physics that we know should drive the energy consumption that aren't currently well reflected in the existing empirical or semi-empirical models. Okay, but welcome your feedback on that. All right, so again, just to re-summarize, the high-level question was how can sustainability metrics be incorporated into existing decision-making processes? We found that simple models can fairly accurately predict various manufacturing outcomes, at least for this use case, and that process preparation software, the slicer or some equivalent of it, is fairly well matched to these types of estimates. So like an equivalent would be for machining, you could do this in a CAM package, right? You could easily estimate the total amount of energy consumption in that. So we're gonna do some human subjects experiments this fall. My PhD student is currently recruiting students to try and understand how the use of this tool can actually impact designer decision-making. We have a fairly passive design right now. You saw that the energy is just displayed next to the material usage. But we can try and push designers a little bit more with different designs. So that's something that we're going to try and look at. There's potential also to look at more holistic measures of sustainability and also to look at social sustainability. We haven't done that, but there's some obvious extensions in terms of the material usage and the environment, material usage and energy usage combined, and looking at the various upstream from cradle to gate, essentially the material and its associated impacts that can be easily incorporated into this workflow. All right, so I'm gonna move on to future work. Something that I'm really excited about is just exploring how DFM tools can be used as persuasive technologies for design for behavior change. So if our goal is to help designers be more efficient, and we've seen that technology can help them be more efficient, can help them make more sustainable or better design choices, lead to improved manufacturability, how can we persuade them to make those choices? In these fairly controlled experiments, we're kind of forcing people to use the tools. How can we actually design the tools so that in natural use, people are going to notice them, react positively to them, decide that the cost outweighs the benefits, and use the tools. So this is something that we're trying to try and draw guidance from psychology, behavioral decision-making, and also HDI to understand how to do better. And then just work on incorporating these into different existing CAD workflows where sustainability and manufacturability information is typically tucked away or not provided in a lot of detail. So I want to acknowledge my PhD students and undergrads. This is related to dissertation work from Bushra and David, and they were supported by a couple of great undergrads working in my lab. And finally, I also want to say a plug, which is I'm hiring for a postdoc. And if you know anybody, I'm assuming you're all very, very happy, but if you know anybody who wants to work on their TAN, please send them to us in Arizona. I have 2 funded positions for graduate students that I'm currently trying to recruit for. So that's the end, and I'd be very happy to take your questions.
Have you tried the same approach in other types of manufacturing and tooling other than 3D printing?
No, but I think that's a really interesting application area, and the extensions would be fairly natural, like I said, for like a CAM workflow for machining. We understand fairly well machining energy consumption, so it would be easy to incorporate it. Although I don't know if some of the CAM workflows, like I think Fusion 360, for example, allows plugins and has CAM instruments in there. So future work, is there a particular process you're interested in?
No, but I've been working with manufacturing before I was a PhD student.
Nice.
So there was a lot of processes to have in mind of if we are looking at the hollow structure, what kind of tools do we need?
Yep.
If the structure has to have a corner, do we need to chamfer it into having a curvature into the piece? Or if we have a wall that is an inclination, how can we direct the tools to have the less chipping? And
yeah, so more automated guidance for tooling specifically, is that kind of what you're saying?
yes, well, kind of like a software or making a process that gives you the best type of the most optimal tooling for the specific dimensions.
Automated tooling design, yeah, very cool. I think that'd be a super interesting application area.
So I have a basic question on the expert side. Sometimes it is not like easy to find some relevant experts and like going from one particular geometry to different ideas. How do you see generative AI based experts fitting into this?
Yeah, that's interesting. I've actually thought about this, like using LLMs to provide high level guidance. I've actually evaluated ChatGPT to give manufacturing guidance, and some of it's not bad. But I think the reliability of that information is very questionable. But one thing that I do like about it is that the conversational style is fairly conducive to the workflow that we saw startup designers like to work with. They liked throwing an idea over the wall and getting a little bit of non-critical feedback. Just, oh, it looks good, or try and adjust this. So I think that there's an opportunity for kind of like a chatbot type thing, but it would need to be trained with different data and higher reliability data where we actually trust and know where the data is coming from.
So you can generate with fairly synthetic data from generative AI, and then you have your high quality data, and then do some transfer learning on that. And
potentially, I think so. When I've used ChatGPT, so, okay, for generative AI, I don't know, I think you would have to look to see the quality of the outputs. I know I saw some work at IDEPC, CIE this summer, where they looked at generative AI capacity to make CAD following specific instructions and specific requirements, and it was pretty horrible, but that was CAD. So I think potentially images might be slightly better, but then you have different perspectives, 3D perspectives, that might complicate it. So you could probably use some amount of synthetic data, but I think you would need higher quality data mixed in. Yeah.
Thank you for a very nice talk. I was taken with that point about how learning about manufacturing and processes could actually even induce some creativity, and I wondered if you could just talk any more about the evidence for that or any hypotheses that you have coming out.
Yeah, so this is something that I was a little surprised to see, but a number of different engineers that we talked to mentioned it. So they were saying that once they had a lot of hands-on experience with a particular technology, they would start to walk around and see objects and say, I bet I could laser cut that. I bet I could assemble that out of a number of 2D laser cut parts. So I think there could be some interesting areas around like design initiation and creativity sparking, where, for example, if a designer gives a rough CAD model, you could give approximate shapes similar to that could be produced via different manufacturing processes. You can decompose it into a number of 2D shapes that could be cut on a laser cutter machine, for example. You could show what it would look like if it was machined. So I think that it's an interesting area for just creative exploration, but on a training and education standpoint, it's a little harder because I think that some process, it's about being deeply acquainted with processes and really understanding what the process is capable of making. And it seemed like the engineers learned that over months, over years, this really high familiarity with its capabilities. So I don't know if it can be easily substituted in the learning process. Does that make sense?
Yeah.
And have you thought at all about like the socio-ethical considerations of the suggestions that the software outputs and how like there's no necessarily responsible party other than the creators of the software as to what the suggestions are?
Yes, yeah, I think there are some interesting questions. I have no idea how to deal with them. That's like the ethics of it, right? The ethics of suggesting and trying to influence behavior feels a little creepy. But it's also a powerful tool that's happening whether or not we utilize it, right? There are inherent suggestions. The makers of Cura currently are suggesting by default a process plan that's probably not sustainable. Is that ethical?
Yeah.
They're doing it unintentionally, but they're still promoting the behavior that's unsustainable essentially.
Yeah.
So I think that we need to understand what the options are and then find collaborators who can help us navigate the ethical questions around that.
Yeah, it definitely should not pause the development of the tool, but I think it's important in building the tool.
Right.
Just recognizing that that can be something.
Yes.
I have a follow-up question. So you collected some of the data yourself and then there was some open data as well. So
Yes.
can you comment on the reliability of the data and how do you figure out the uncertainties that come with that?
Yeah, so the biggest issue that we had, there were two issues. One was data that was reported inaccurately. Another was missing data. So we did data imputation where we tried to collect, I think it's a set of like 15 or so variables, and for about 7% of our data there was some value missing, and we used the Cura defaults, or we inferred based on other information in their it's from papers, from their papers, what we thought the best guess would be for that data. We also found mistakes. I actually emailed a number of authors of papers and asked them for clarification and found errors in many of them because the order of magnitude is roughly the same for many of the printers, depending on printer size and characteristics. So we back checked it. Is this a reasonable estimate? And if it wasn't, we contacted them and got a correction, or we threw it out. So it was fairly manual.
Have we
write like the energy estimation for the metal printing apart from FFF, like for SLM or for LPPF?
Yes, I haven't, but I think that there's opportunity to do so because a lot of the same concepts apply where build time is really important to estimate accurately in order to understand the energy consumption. So that's the first step. And there's actually not a ton of open source ways to estimate build time. So we would probably have to embed it in a tool kind of like this, but for the powder bed fusion workflow.
Yeah, because I am curious to understand like how, when we change the laser power, hatching speed and scanning.
Right.
Like different stuff.
Yes,
Energy consumption.
it'll make a difference, yeah. Mhm.
In the slide where you have your chain of sort of going from concept all the way through to sort of the detail design, how far upstream do computational tools, good computational tools at least, exist to aid a design or a design?
Really, everything, including most of my tools, requires some type of CAD input. So not very far up. I think like we can do cross sections in some of these, but right now the way we're generating the cross section is by having a CAD model. So there aren't a lot of tools currently that can give any kind of DFM information based on a sketch. So they don't go very far up. They require some sort of CAD model. But I think there's the possible, something that I'm very interested in is pick a similar part from our library or describe a part, and then maybe using some sort of generative processes, we come up with a rough estimate of what you think that part is going to look like, the material it's going to use. What are the minimum viable list of characteristics that we need to get a rough order of magnitude estimate for these types of things? You know, give me the bounding box size, give me a description of the complexity, we'll come up with a rough CAD model and then make estimates based on it. I think that's really interesting, but that's something that's not going to happen next year.
Last questions for speaking? Awesome. Well, let's thank her one more time.